Hey everyone, welcome. Today we're tackling a Leetcode problem called Find the Maximum Sum of Node Values. It sounds a bit tree-heavy, but we'll see there's a really neat trick to it. Let's break it down step by step. So here's the setup. We have a tree of nodes, and each node has a value. We're also given a positive integer, let's call it. The main thing Alice can do is pick an edge connecting two nodes, say. And when she picks an edge, she changes the values of both node and node by XORing them with. She can do this as many times as she wants. Our goal is to figure out the absolute maximum sum of all node values Alice can achieve. The inputs are the list of initial node values, which we can call the integer, and the list of edges that define the tree. Let's walk through the first example. Suppose our node values are 1, 2, and 1, and our special number is 3. The tree connects node 0 to 1, and node 0 to 2. First, let's see what happens if we XOR each node's value with which is 3. Node 0 has value 1. 1 XOR 3 is 2. Node 1 has value 2. 2 XOR 3 is 1. Node 2 has value 1. 1 XOR 3 is 2. Now, if we could just pick the best value for each node independently. For node 0, 2 is better than 1. So we'd pick 2. For node 1, 2 is better than 1. So we'd pick 2. For node 2, 2 is better than 1. So we'd pick 2. This would give us a sum of 2 plus 2 plus 2, which is 6. Notice here we decided to XOR node 0 and node 2, but not node 1. That's two nodes being XORed. We'll come back to why that number is important. The example output is indeed 6. Okay, let's think about that operation. When Alice picks an edge between, and both their values get XORed with, what if Alice performs this operation along a path? Say, from node to then to first. Operating on the edge changes, and so becomes A XOR K, and becomes B XOR K. Then, operating on changes and becomes C XOR K. But which was B XOR K, becomes B XOR K, XOR K, which is just again. So the nodes at the ends of the path, and get XORed. Any intermediate nodes, like are XORed twice, so their values effectively don't change. This is super important. It means Alice can pick any two nodes in the tree, find the unique path between them, perform the operation on all edges of that path, and the result is that only those two end nodes have their values XORed with. So Alice can pick any two nodes and flip their XOR state with. Think about it. Each fundamental operation on an edge affects two nodes. If a node is involved in, say, 3 such edge operations related to it, its value will be XORed because 3 is odd. If it's involved in 2, its value won't change overall because 2 is even. Every time Alice performs an operation on an edge, it's like 2 are distributed. The total number of these across the whole tree must be even. This leads to the crucial insight. The total number of nodes whose values are actually changed by, at the end of all operations, must be an even number. It can be 0, 2, 4, and so on, but never an odd number. This is key. The tree structure just guarantees we can achieve this for any even set of nodes. The specific edges don't really matter beyond that. So here's the strategy. First, for every single node, we look at its current value, and what its value would be if it were XORed. With greedily, we'd want to pick the larger of these two values for each node to add to our running total sum. While we do this, we also count how many times we picked the XORed value. Let's call this the XOR count. And, very importantly, for each node we calculate the difference between its original value and its XORed value. We find the smallest absolute difference among all nodes. This is like the smallest, or if we're forced to change our mind about XORing one node. Now for the twist. If our XOR count, the number of nodes we chose to XOR, is an even number, then great. Our greedy sum is the answer because we're allowed to XOR an even number of nodes. But, if the XOR count is odd, that's not allowed. We must change our decision for one node to make the count even. To keep our sum as high as possible, we should make the change that hurts us the least. That means we subtract that smallest absolute difference we found earlier from our greedy sum. Let's formalize that into steps. 1. We'll start with a max sum of 0. 2. We'll also count the nodes chosen for XOR, starting at 0. 3. And we'll keep track of the minimum absolute effect of a flip, starting at a very, very large number, like infinity. 4. Then, we loop through each node. For each node, A, get its original value and its potential XORed value. B. If the XORed value is greater than the original, we add the XORed value to our max sum, and increment our count of nodes chosen for XOR, D. Otherwise, we just add the original value to require max sum, D. No matter what we chose, we calculate the absolute difference between the XORed value and the original value. If this difference is smaller than our current minimum absolute effect of a flip, we update it. 5. After checking all nodes, if our nodes chosen for XOR count is even, we just return the max sum we've built up. 6. But if that count is odd, we return our max sum minus the minimum absolute effect of a flip. And that's the whole algorithm. Alright, here's the Python code that implements our strategy. It might look a bit dense at first, but it follows our logic exactly. We'll walk through the key parts. Don't worry, it's simpler than it looks. First up, we initialize a few variables. Potential max sum starts at 0. This will hold the sum we get by greedily picking the best option for each node, either its original value or its XORed value. XOR preferred count also starts at 0. This will count how many times we chose the XORed value because it was larger. And minimum penalty to flip parity is set to a really large number, essentially infinity. This will store the smallest absolute difference we find between a node's original value and its XORed value. This is the smallest we'd take if we have to change one of our greedy choices. Next, we loop through each node in our list. Inside the loop, for the current node, we get its original value and calculate its value by XORing it with. Then we check if the value is greater than the original value. If it is, we add the value to our preferred count. Otherwise, we just add the original value to the Finally, for this node, we calculate the when. We then update our overall we this node After the loop finishes, we have our potential max sum and the XOR preferred count. Now we do the final check. We see if the XOR preferred count is an even number. Remember, the remainder when divided by 2 tells us this. If it is even, then our potential max sum is achievable. And that's our answer. We return it. But if the XOR preferred count is odd, our current sum isn't valid because we're only allowed to XOR an even number of nodes. So we must adjust it. We take the potential max sum and subtract the minimum penalty to flip parity that we carefully tracked. This subtraction effectively flips one node's decision, making our count of XORed nodes even, and does so with the smallest possible reduction in sum. So how efficient is this approach? For time complexity, we basically just loop through the list of node values once. If there are nodes, this takes about steps. So we say it's big O of n or order n time. That's pretty fast. For space complexity, we're only using a handful of variables to store our running sum, the count, and the minimum penalty. This doesn't depend on the number of nodes. So, it's big O of 1 foot, or order 1 space, also known as constant space. That's really good too. The list of edges isn't even used in this calculation, which is neat. So to wrap things up, the biggest takeaway is that sneaky rule. No matter what operations Alice does, an even number of nodes will end up having their values XORed with. The fact that it's a tree structure is what makes it possible to pick any even set of nodes to be XORed. Our strategy then becomes pretty straightforward. For each node, we greedily pick whether to use its original value or its XORed value, whichever is bigger. If this greedy choice leads to an odd number of nodes being XORed, we just need to make one small correction. We find the node where flipping our decision, from XORed to not, or vice versa, costs us the least, and we make that flip. This ensures an even count and the maximum possible sum. Hope that breakdown made sense and helped you understand the problem. If it did, feel free to hit that like button, subscribe for more explanations, or drop a comment if you have any questions. And hey, if you're feeling extra generous, there's always the Boba Fund. Keep practicing, keep coding, and I'll catch you in the next one.